Hello everyone. In this video, we'll be discussing the chemical properties of metals. So how do metals react with various other compounds and other metals and non-metals? That's what we're trying to find out today. So first one, we want to see reactions with air. So how does a metal react with air? Metals can be burnt in air to give you a metal oxide. So metal plus oxygen, when you burn it, will give you metal oxide. Now, a classic example for this would be aluminium. So Al plus O2 gives Al2O3. Now to balance this, we have 3 here, means it has to be 2 here, this is 4Al. Alright? So burning aluminium in air will give you aluminium oxide. The same thing with copper. So Cu plus O2 gives CuO. That's 2 here, that's 2 here. So copper oxide, aluminium oxide are some of the oxides that are formed when you burn a metal in air. Alright? Now we know that metal oxides are basic in nature. So metal oxides can react with an acid to give you a salt and water. So let's take copper oxide. CuO plus HCl gives CuCl2 plus H2O. Alright? Now CuCl2 is a salt, we have water, we have an acid, and we have a metal oxide. So is this true for all metal oxides? In general, yes. But there are certain metal oxides like aluminium and zinc oxides which can react with both metals and with non-metals. How does that work? Let's see. Al2O3, aluminium oxide plus HCl gives AlCl3 plus H2O. Now let's balance this. We're looking at, so this is as expected because aluminum chloride is a salt and you get water. But what happens if you react aluminum oxide with a base? Let's try it with sodium hydroxide. Gives NaAlO2. Now this we said was a basic oxide, but it still is reacting. Alright? So that's balancing. Now you can see aluminum oxide reacts with both an acid and a base. So aluminum oxide is an amphoteric metal oxide. It can react with both acids and bases. Okay? So even zinc oxide can do this. So Al2O3, ZnO are amphoteric. But in general, metal oxides are basic and they react with an acid. Okay? Most of the metal oxides are insoluble in water, which means they can't be dissolved. So if you put water on a metal oxide, it will usually not dissolve, but some of them like sodium hydroxide, sodium oxide and potassium oxide are soluble in water. Now they react to form a hydroxide. So Na2O plus H2O gives 2NaOH. Alright? And K2O plus H2O gives 2KOH. Okay? Now these are all aqueous solutions. But these are alkalis straight. So metals don't always react in air at the same rate, right? Now I said aluminium and oxygen, you have to burn them in air, right? They're not going to happen on their own. But there are some metals like sodium and potassium, which all you need to do is leave open and they will automatically react. Sometimes they even catch fire. So to prevent this from happening, you store sodium, potassium, lithium, the alkali metals under kerosene, because kerosene coats it completely and there is no oxygen available, so it doesn't react. So these metals are more reactive. Some metals like sodium and potassium are more reactive than aluminium and zinc, and then some like copper and gold especially, don't even react. Okay, so this is how they react with air, and we also saw how they dissolve and things like that. Now, how do metals react with water? Reactions with water. Like I said, some metals are very vigorous in their reaction. They can react instantaneously. Some metals, not so much. And some metals will not react at all. So let's see some examples for that. What about sodium? Sodium reacts with water to give sodium hydroxide plus hydrogen gas. Okay, so metals in general react with water to give you hydrogen and a hydroxide or an oxide, usually a hydroxide. So sodium, it can happen at any kind of temperature. Even if it is very low, the reaction happens. The same with potassium. But what about calcium? Calcium can also react with water when it's cold, but it does not release so much heat that hydrogen can catch fire. Many times sodium and potassium catch fire because the hydrogen catches fire. Calcium not so much. Calcium does not catch fire, but it still reacts at cold condition. Okay. Magnesium, on the other hand, Mg, does not react with water when it's cold. It has to be hot water. So magnesium reacts with hot water to form magnesium hydroxide plus hydrogen, but this has to be hot. Then you have metals like aluminium, iron, zinc that can't react with cold or hot water, but they do react with steam. How is that? Let's look at aluminium. 3 moles of water gives Al2O3, yes, plus 3 hydrogen. How does that happen? This happens, okay, so water over here is liquid, but this has to happen with steam, with water vapor. Okay, and like I said, most cases you get hydroxide, but some cases you get oxide. This is the same with iron as well. And metals like gold, which is Au, silver, which is Ag, platinum, they do not react with water at all. So these metals are called noble metals, and most of these are used in making jewelry because we can wear them without worrying about damaging them. Okay, how do metals react with acids? So let's talk about reactions with acids. Metals react with acids to give you a salt plus hydrogen. That is something we've studied in the acids and bases chapter. So metal plus acid gives salt plus water. That is in general. But please note, some of the acids don't give you, they give you salt and hydrogen. Some metals with nitric acid give you salt and water. Because nitric acid is an oxidizing agent, it immediately oxidizes the hydrogen produced into water. Okay? So the rate of reaction again is different based on which metal you're talking about and which acid you have. But in general, for a strong acid, your alkali metals are more reactive and then the other metals come less reactive. So you can see that with the rate at which hydrogen gas is liberated. Okay? So finally, reactions with other metal salts. Now this is something we've done. We spoke about having an iron nail dipped in a copper sulfate solution. So I will put a link to it below, which speaks about displacement reaction. So in general, a more reactive metal can displace a less reactive metal from its solution. Okay? So this is very simple. Iron and copper, lead and copper, we spoke about this in the previous class. But how do you know which metal can displace which other metal? For that, we have to understand what is called the reactivity series. The reactivity series is a table in which elements are arranged in order of their reactivities. So you start with potassium, and then sodium, and then calcium, magnesium, zinc, iron, lead, hydrogen, copper, mercury, silver, gold, and platinum. So these are highly reactive. These are intermediate, which is medium reactive, and these are poorly reactive. So how do you know whether which metal can displace another metal? So let's take iron. Any metal above iron can displace iron from its solution. If you see copper and iron here, so iron can displace copper. So basically, the lower you are in this series, any metal above can displace it. Okay? So this is how the reactivity is arranged. And this arrangement is called the reactivity series. Alright? But why is this the case? To understand that, we have to understand the electronic configuration of these elements. Okay? So let us discuss how do metals and non-metals react. That's a very simple question. The reason they even react to begin with is because of their electronic configurations. Alright? Now think of a non-metal like oxygen. Alright? You might have studied the electronic configuration in your previous classes. The atomic number of oxygen is 8. So you have 1s2, 2s2, 2p4. Now we know that neon is 1s2, 2s2, 2p6, and this configuration is stable. So if you notice, oxygen requires 2 electrons to reach the electronic state of neon, and that is what it wants to do. So oxygen likes to pick up electrons from something else. Now consider lithium, which is an alkali metal. The electronic configuration of lithium is 1s2, 2s1, and the closest noble gas to lithium is helium, which is 1s2. Okay? So now we know this is stable, but lithium has 1 extra electron. So lithium likes to give away its electrons, whereas oxygen likes to take up electrons. Okay? That is why lithium is stable as Li plus, oxygen is stable as O2 minus, because O2 minus with 2 extra electrons is the electronic configuration of neon, and lithium plus with 1 less electron is the electronic configuration of helium. Okay? So metals in general tend to form cations by losing electrons, whereas non-metals tend to form anions by gaining electrons. Okay? So what are cations? Cations are positive, anions are negative. Okay? So metals tend to form cations, non-metals tend to form anions. Now, if a metal comes in contact with a non-metal, then there is a complete electron transfer. When a metal comes in contact with a non-metal, complete electron transfer takes place. How does that happen? Let us consider sodium chloride. Okay? So sodium has an NS1 and chlorine has an NP5. Okay? So we know, or let's not take N at all. The outermost electronic configuration of sodium is an S1 and of a chlorine is a P5. So the easiest thing to do is for this electron to be completely transferred there to allow chlorine to get a P6 and a sodium to get an S0, or which is a previous P6. Okay? So that way both these can attain noble gas configuration and they can become stable. So Na, when it comes close to chlorine, will become Na plus and chlorine will become Cl minus. Now you know that positive and negative charges attract by a strong electrostatic force. Okay, so there is an electrostatic force between a cation and an anion. In this case, a cation is Na plus, the anion is Cl minus. So this electrostatic force is called an ionic bond. Some people also call it an electrovalent bond. Okay? So how does this happen? Let us draw the electron dot structures of these two. So Na has 1 electron, chlorine has 5 electrons in its outermost shell, or 5 electrons in its outermost subshell, but 7 electrons in its outermost shell. So what happens is this gets transferred completely to give you Na with nothing or a positive charge, and chlorine with a negative charge with 1, 2, 3, 4, 5, 6, 7 and 1 extra electron that it picked up from sodium. So this is how an ionic bond is formed. Okay? Now what I said before was it is held together by a strong electrostatic force. Electrostatic force is very strong. It is one of the strongest forces in nature. Okay? So what can we say the characteristics of an ionic bond would be? Let's see. Ionic bonds have certain properties because of their strength. So properties of ionic compounds. First and foremost, like I said, they are extremely strong. So they make hard, brittle solids. Think about sodium chloride, the common salt that we eat. It is hard, but it is brittle. It's easy to break, but it is hard. Okay? The second one is they have extremely high melting and boiling points. Why is this? Because of the electrostatic force of attraction. The strength of the forces is so high that you have to supply a lot of heat before they melt to break that force. Okay? So that is why they have such a high melting and boiling point. So what else? Third one, because they are inherently formed by ions, you have a plus and a minus, they are soluble in water but insoluble in organic solvents like kerosene. Okay? And finally, when they are in solution or when they are molten, they can conduct electricity. When they are solids, the electrostatic forces are so high that they cannot move. And if they cannot move, they cannot conduct electricity. When in solution or in molten state, the ionic bonds are free enough to allow movement of ions. So they can conduct electricity. So these are the properties of ionic compounds, and in general, when a metal reacts with a non-metal, an ionic compound is formed. When a non-metal reacts with a non-metal, we get a different kind of compound called a covalent compound, which we will discuss in the next chapter. Alright, thank you.